Okay, so in this video we're going to be talking about the general rules of differentiation as we discussed in the previous video. So one of the very important rules is when we have a polynomial, maybe something that's of x to the power n form. If we were to find the differential of this, let's call this f of x, right? So the differential f of x, f dash of x, or basically dy by dx, is going to be represented by the power being multiplied by the entire term, and the term will be written as it is, but its power will be decremented by 1. So that's kind of like a general rule. So if we have like a few examples over here, maybe if we have 2x squared, we will bring the power to this part and multiply it by whatever is there. So it's going to be 2 times x2, but we know that we've applied the differentiation rule, right? So we're going to decrement it by 1. So it's like kind of like a general rule to remember. So the differential of 2x squared turns out to be 4x. And if we were to apply this to lots of different terms, we get 4x squared plus 9x cubed plus 1. What we get is essentially, we bring the power over here, we get 2 times 4 times x2 minus 1 plus over here, because the differentiation operator could be applied to a sum. So basically the differential of a sum equals the differential of the individual terms that are involved. So over here we're going to get 3 times 9, 27 x squared. And the different part as to why 1 gives us a differential of 0 has been discussed at length in the previous video, right? So the differential of a constant gives us a 0. So the answer over here is 8x plus 27x squared. After a while, you guys will get used to this idea and simply take the differential directly by just doing it in your heads, right? And I look forward to that time. But for now, let's just do it step by step so it makes more sense. So that's the first case over here. Then we have the differential of a constant function, which we know always evaluates to what? Yes, exactly, a 0. Derivative of a constant function at any value of x, by the way, has to be equal to 0. Another important case that we should talk about at this point is could be represented by the exponential function, right? If we have the exponential over here, right, and we try to differentiate it, it's going to reproduce the function itself. So the differential of e to the power x gives us e to the power x. This is kind of unnecessary at this point because we're going to be covering the exponential function in much more detail, but I just want to state this fact at this point in case we need it to use in the later videos, even before we cover the topic of exponential. Another important thing that you guys should note down for the first particular case is that this could be applied to any value of n. So if you have something weird like I don't know, if the function kind of looks like x to the power 1 over 2, then evaluating this would simply give me 102 times x to the power 101, right? And if I were to find the tangent now at that particular point, I could do that as well, but I'm going to be covering tangents in much more detail in the next video. So let's look forward to that over here. But if the differential was to be determined at a particular point, for example, if x equals 1, so I'd simply plug in a 1 over here and I'd get the differential at the point 1. And this turns out to be 102, right? So this is a simpler case of that. And another important case that is not really covered is the square root x function, right? So if you think about it, the x to the power n rule, does it apply over here? Well, simply put, root x is the same as x to the power 1 over 2. So we could try and apply the rule over here. So we bring the power close to that part, right? And we write x as it is to the power, but we subtract a 1 from here, right? And if we do that, we're going to get x to the negative 1 over 2. So what's going to happen is 1 over 2 is going to remain the same. We're going to get x to the negative 1 over 2. But I'm going to just flip that, right? And write it as x to the 1 over 2, because that's what happens. If you have a negative sign, you could just flip it and change the exponent sign and you'd get the same value. And 1 over x to the power 1 over 2 is going to give me 1 over root 2. Actually, 1 over 2 times root of x, right? So that's a different way to think about it. Another very important case is the reciprocal function. The reciprocal function looks like 1 over x, right? So what if we were to find the differential of this, right? What would we do? Well, we'd re-express this as x to the power minus 1 because we know we can do that, and then try to, approach things from there. And this is a very important technique, guys. You might want to just get it down at this point, the reciprocal function, because this will be used in later trigonometric identities, and not just identities, in differential rules as well, and examples in which this could be utilized to make your lives a lot simpler, right? So if we try to find the differential of this, we get minus 1, because that's the power that's going to come down, right? Minus 1 times x to the minus 1. But we know that we have to decrement a 1 regardless of this value. So we get that. And if we rewrite this, basically we get minus 1 times x to the negative 2. But we can just flip that, right, by reversing the sign as well. So we get minus 1 times 1 over x squared, which is basically minus 1 over x squared. So the differential, or d by dx of 1 over x, the reciprocal function, gives us 1 over x squared and a negative sign with that. So this is kind of an important rule. So that's pretty much it for this video. In the next video, we're gonna start with the idea of tangent lines and see what we can do by relating the rate of change concept to a tangent line. See you guys then.